At the beginning, so this is where the ion source is. So we have two ion sources. So these are ECR ion sources which produce high charge states. So when one is running, the other one is prepared so that the changeover is slow. Then it comes in here, and then it can go into this cyclotron, and then after accelerating with this cyclotron, you can go to the next one and then do whatever you want. I'll come back here. So now one thing you can do here is this. When this is running here, you can use the ion source to go to this IR suit. So you do low energy experiments here, which include surface studies and material science or implantations or other stuff. So this is some solid state physics sort of stuff which goes on here. Then you can also go through this, and part of the beam can go out. So this is around 14 MeV per nucleon. You can go out here. So the part of the beam can go here, and you can go out here, and you can do some atomic physics and other studies out here. So where they go, all this stuff is there, and I will come to that. Okay, so this is just the accelerators, which we will see this. This is CSS1. Okay, then you have to increase the charge state of the beam, so you strip it somewhere here. Okay, so you get a higher charge state. So if you have a higher charge state, you have more energy gain. So then you go through the second one, and then you go through this alpha separator, and then you go to A, and A is here, which means you can go to any of the beam lines in GANIL. Okay, so that is, if you just send a standard high energy stable beam, you can do that. Part 2, so now we come to what is the ISOL stuff. So you want to produce short-lived around millisecond or tenth of millisecond. Then you take that beam, okay, that high energy beam, you go and bang this here. So this is a thick target, but made with large surface area, so things come out. And then you ionize the stuff here, you bring them out, you do some pre-selections in M/Q, and then you send it into the seal cyclotron, where you can accelerate this. This can go to a maximum of 25 MeV per nucleon. These are total is 95 MeV per nucleon, just to give you the scale. And then you go back to the same alpha, and you back to A, and then again you use the same stuff. Then if you want to use directly the radioactive ion beams without acceleration, so there's a small acceleration of 60 keV, you can go to this Lirard line, where you can do fundamental physics studies. Then so this is what we are going to see, and then in this scale, spiral 2 is somewhere here. Okay, and it will, so after you produce it here, it will come back to this cyclotron, and then come back to the back to A. Okay, so these are the radioactive ion beams. The stable beams from spiral 2 stay in spiral 2, they have nothing to do. So this is independent in that sense, otherwise it is dependent if you use radioactive ion beams. Any questions, clarifications? No? So now first we will go, okay, so let me come here. So the labeling, you can see D and G, this is gauche and droit, that means left and right of the beam. And so it is split this way, and then there is what we call the fishbone, which sends the beams to various places. And then we will see this, this. We don't have permission to see this. This is the least spectrometer, which you can't see because there is some little, there's a target here, so they don't want visitors.
The idea is that when people are coming, so like for example here we have just one active dosimeter for all the group, but for physicists who are working on the area, we have an active dosimeter and also a passive dosimeter. And this passive dosimeter, for example, this one is if we just put an increase of the radioactivity rapidly, we have to go outside the area, etc. But this one is checked every 3 or 4 months, something like that, and we don't have to exceed 2 millisievert per year. So I don't know if it's something very clear for you what is 2 millisievert per year. For example, with the law in France, it's 20 millisievert per year for people who are working in EDF, Electricity of France. Okay, so you see it's very low, so there is not a lot of risk to working at GANIL. And for example also, so it's, as I tell you, it's 2 microsievert per year, and coming from the cosmic ray or to the Earth, we have each year 1 millisievert per year. So it's just 2 times what. Okay. So now we are here in the experimental area. So as Navin told you, when you are sit on the beam, on the right side, in French we say droite. So you are zone D1, D2 for droite 1, 2, etc. And on the left, gauche in French, we have G1, G2, etc. So here we are in D5. So this is a detector Indra. So I'm not an expert of this detector, but it's more or less beautiful. So that's why we show this detector. So it's a detector for to study hot nuclei. So nuclei with high temperature and at the limit of what we call name a nucleus. And this is a detector which is composed of 17 rings, and each telescope, so one telescope is defined like, you see, this one is telescope, this one another one, etc. And one telescope is composed of one ionization chamber, one silicon, and one CSI detector. So I know that you have a good selection in Z of this nucleus, and this kind of detector to study this hot nuclei, and it's a fixed detector in this room. So it's a room dedicated to this detector. This detector is always here in GANIL, okay? And with all its own electronics. So this is the electronics of Indra, just right there. But it's dedicated electronics. That's it. You can't put a module and do another experiment. No, okay? It has its electronics and its detector stable in this room. And this detector has 20 years ago, I think so.
The beam comes from that?
Yes. Beams come from that direction, enter here, and you have the target at the middle of the detector.
So they open it every time I put the target in?
Yeah.
And they set it up in?
You put the target, you close the chamber to the vacuum, and send the beam to the detector. Okay, we'll see another one. You have a question? I'm not sure that I will answer because I'm not an expert at all on this detector. But
no, I was wondering in which devices we can use to measure some properties of two nucleon transfer reactions.
Two nucleon transfer reaction. SUSO, your analysis. So for transfer reaction, we are used to some more. There was a big campaign last year.
Yeah.
So for this analysis of his PhD was during this campaign, and it was transfer reaction, so 1 or 2 nucleons.
Okay.
And they used. Okay, now it's finished, so we will not see the setup. But they use 2 trackers to track the beam direction.
Okay.
They sent it to a target surrounded by silicon detector, and there was also germanium detector and a chamber to stop the beam, etc. But you can ask me the question to Suzo, you know perfectly this setup.
Do you know what this is? This one?
I think? No, I don't know. Okay, I don't know. Maybe the first.
Plus two. Plus two. But because Indra was used, a part of Indra has been used in small for another experiment.
I don't know. Okay, I don't know.
But I don't know. I don't think it's part of Indra. Because Indra is more or less complete. Maybe that's. I think there is a ionization chamber missing.
But I have read that there is the first string, so the first string at the beginning of the beam entrance, maybe this one, and it's plastic and not ionization chamber, silicon and CSI, so maybe it's that.
It's part.
Maybe it's, yes. And they have to make it
So. I'm sorry.
We'll see later. This is a part of the GANIL now, and this is experimental area. So the beam is accelerated in the accelerating building that we will see after, and enter here in what we called the fish bones, because it look like a fish bones, okay? And so the detector Indra we just see is here. So we have worked like that. So this is a D6 room. Is a room where I am explaining that there is a setup with the beam tracker, the silicon, etc., where Suzo has done his experiments few months ago. Okay, and Navin just told you also that this D6 room is the least beam line, is the only line in the GANIL, actual GANIL, in which we can do fragmentation. Okay, everybody in the other, everywhere in the other experimental room, we can do isol facility, so to use this spiral 1 beam, so isol beam, or stable beam, but the only room in which we can do fragmentation is this beam line. So we accelerate the stable beam. There is at the entrance here a target, fragmentation target. There is a cocktail beam after this target, and the nucleus, the unstable nucleus you want to study is selected in this new spectrometer and then sent to this room after that. But now there is no detector here, so it's not really interesting. So now we are just here at the end of the fish bones. So we'll try to answer in this way at the end of the fish bones to see all the interests of the different areas. From in this line, so you have all these dipoles that give the good trajectory you want to go in. So these dipoles are giving a magnetic field that will change the curvature of the trajectory of your beam. Okay. And there was also quadrupole, which are the small elements here, for example, which are used like lens in optics to focus your beam. Okay. So you have dipole to give a curvature to your trajectory, and quadrupole to focus your beam. Okay. And you can see that, for example, this line is to send the beam to the Indra room. So the room is the Indra room, which just have seen before. Okay, go back. But not happening to book or read. Okay, do you have some questions concerning these fish bones?
Is that supposed to interrupt?
Yes, it was when you asked me how it was.
Yeah, so just
yes. Fine. Okay. And the dipole you see in the same hole there is the entrance of the spectrometer. Okay, we can go out. Is to hit this target to have a gas at the end. This gas is sent there in the ECR ion source, so it's for electronic cyclotron resonance source. Okay, that it means that your gas, which is very hot, is sent to this box where you send radio frequency. Okay, radio frequency, and in this radio frequency we will grab an electron from the atoms. Okay, so at the end we have a plasma with all your atoms that are ionized, and so you have atoms ionized and so electrons that are moving in this plasma. Okay, this plasma is confined with magnetic field, and so you have your plasma, your magnetic field, and you have an extraction voltage to put out your atoms which are ionized. And since they are ionized now, you can accelerate it, because if you have a zero charge, you can't accelerate your particle. Okay? So this is done with a CR ion source there. You extract your ionized particle and then send to the first cyclotron, C0, here. And at the end of this cyclotron, you have a velocity of something like 1,000 kilometers per second. Okay. And after that, these ionized particles are sent to the next cyclotron, CSS1, that we'll go to see now. Stop me if you have some question. Not a lot of some things to do to say in this room because we have not access to this iron source big, but this is the beginning of the story of the travel of the nucleus. Okay? So this is up to now is stable beam. Okay? Because we have stable source that we eat, we ionize, extract ions, send to the first cyclotrons, and send after that in the second cyclotron.
Where come from the power supply of this facility? Usually from the... there is a special power supply?
I think not far from here there's a nuke power center. And you have to know that the GANIL is using a lot of these powers. Actually, I think the GANIL is not running in special period of year, like in special time in winter, because it's consuming half. I mean, if you include all of half is coming from the GANIL. So GANIL is consuming as much power as 200,000 inhabitants. If you want to have an idea. I couldn't get I don't have the figure in watts, but to give you an idea of what's represented. It's the same as a city. Yeah, it's a lot.
Please. Thank you.
Okay. So we have seen that our stable beam is first accelerated in the first cyclotron C0 and then sent to another cyclotron CSS1. So at GANIL we have 5 cyclotrons, 4 up to CSS2. So C0 we have the same C1 for 2 ion source. After that we have 2 big cyclotrons, CSS1 and CSS2. And after that, we have another one called SIM for the spiral line, so ion facility. But we will not see it because normally I will have to finish now about the visit. Okay? So this is the first big cyclotron, CSS1. CSS2 is exactly the same. Okay? And so the beam is sent to this cyclotron. So CSS1 is for cyclotron à secteur séparé. Separated. Voilà. Okay. So everybody know how a cyclotron works, more or less, or it's yeah. Okay. So firstly, you have your particle which is charged with a positive charge enter in the cyclotron. If it's in a negative charge, it will come here, and after that we change the polarity, so you put a negative here and a positive here, so it changes another way, etc. So if we do like cycle like that, but if we don't put any magnetic field, your particle goes away. So you need a magnetic field that your coverage, your trajectory stay around the cyclotrons. Okay? So 2 things in a cyclotrons, a magnetic field to confine your trajectory and an electric field to accelerate your particle. Okay? So this cyclotron is composed of four electromagnets. Okay? So this is a big magnet, and each magnet has a weight of 4,000 tons. Si je fais bêtise. Okay? So these are big cyclotrons. Okay? So you have 4 magnets that are able the force to give 4 Tesla magnets compared to the Earth's magnetic field, which is about 10 minus 4 Tesla. Okay? So this is 4 Tesla in the cyclotrons. And so this is for the confining particle. And concerning the acceleration of the particle, so as I tell you, we use electric field. So this is done in 2 accelerating cavities, okay, which are not really easy to see in this cyclotron, but we have a model just here. So this is exactly the same accelerating cavity that you have in this cyclotrons, but this is the scale 1/4. Okay? And so this is in the center of the cyclotron, and your particle just enter in the cyclotron, see a first time an acceleration here, do a turn, see the other one on the other side of the cyclotron, etc., etc. And if we remember your study, your lesson concerning the magnetic field, etc., etc., you will maybe remind that in the cyclotrons, the angular velocity is constant. Okay, that it means that when your radius is increasing, your velocity also is increasing. Okay, so at each turn, you increase your radius, and at the end, you actually have at the biggest radius, you have the biggest velocity. Okay, and so at the end of CSS1, we have a velocity of something like 10,000 kilometers per second. And at the end of CSS2, so just before sending it to the fish bones we have seen before, we have a velocity of 100,000 kilometers per second. Okay, so 1/3 the light velocity. Okay? It's okay?
So light percentage of light speed. How
What the percentage of the
Yeah, in
Light-
terms
yeah.
of
light speed? 1/3.
one over
Yeah.
Okay, now
Yeah.
Yeah, 1/3. Okay. Which is big, but not so big compared to the CERN velocity, for example.
Yeah.
Okay. So yes, the nucleus, the ionized atoms that come in this cyclotron is doing something like 100 or 200 turns in this cyclotron, and then the second cyclotron is doing something like 300 turns before sent to the fish bones. So at the end, between the beginning of the solid source or the gas source and your detector, the accelerated nucleus has done something like 10 kilometers with all this turn in the cyclotrons. But you have seen that this is something like at maximum 100 meters between the two areas. Okay. Another point we used. So we have seen, and you can see also these dipoles, this quadrupole, which are the really useful element to travel your beam on the different cyclotrons, and then after that on the experimental area. Okay. I would like to mention.